These are the answers to the AP Chemistry packet that covers topics 3.5 to 3.8. On this slide, you can see Unit 3 at a glance. Unit 3 is entitled Properties of Substances and Mixtures. In this video, we will take a look at Topic 3.5, Kinetic Molecular Theory, Topic 3.6, Deviation from Ideal Gas Law, Topic 3.7, Solutions and Mixtures, and Topic 3.8, Representations of Solutions. In the video description area, there is a link to the AP Chemistry course and exam description, which we call the CED for short, and there is also a link to the packet that accompanies this video. Topic 3.5, Kinetic Molecular Theory. Here are some essential knowledge statements from the AP Chemistry course and exam description. The kinetic molecular theory, or KMT, relates the macroscopic properties of gases to motions of the particles in the gas. The Maxwell-Boltzmann distribution describes the distribution of the kinetic energies of particles at a given temperature. All the particles in a sample of matter are in continuous random motion. The average kinetic energy of a particle is related to its average velocity by the equation Ke equals 1/2 mv squared, where Ke is kinetic energy, m is the mass of the particle, and v is the velocity of the particle. The Kelvin temperature of a sample of matter is proportional to the average kinetic energy of the particles in the sample. The Maxwell-Boltzmann distribution provides a graphical representation of the energies or velocities of particles at a given temperature. So in the previous video, I had talked about the properties of gases, and here you can see on this slide a video clip from the PhET simulation on the properties of gases. So I can put a link to that PhET simulation in the video description area. The following statements were listed in the previous packet in topic 3.4, Ideal Gas Law. These statements summarize the kinetic molecular theory. Gas particles are in constant, random, rapid motion. Gases expand to fill their container completely. Two or more gases will form a homogeneous mixture when they are combined together. Gases are highly compressible. The volume of the gas particles themselves is negligible compared to the volume occupied by the gas. Collisions of gas particles are perfectly elastic, meaning that energy is transferred but not lost during collisions, and there are no attractive or repulsive forces between the gas particles. Consider two different samples of gas, hydrogen and oxygen, at the same temperature. The absolute temperature of a gas is a measure of the average kinetic energy of its gas particles. Since these two gas samples are at the same temperature, the gas particles in each sample have the same average kinetic energy. But let's take a look at the relative speed of gases where they have different masses. The masses of the particles are different. Here, in this PhET simulation, we have a mixture of two different gases. One of them, the particles are heavier. So the heavier particles have a slower average speed, and the lighter particles have a faster average speed. If we consider the kinetic energy equation, where Ke equals 1/2 mv squared, m equals mass, and v equals velocity, we can see this inverse relationship between mass and velocity or speed. So the gas that has a smaller mass for the particles is going to have a larger value for the velocity or the speed. And on the other hand, if a gas has a larger mass of the particles, it's going to have a smaller velocity or speed. So if I have two different gases at the same temperature, the gas with the smaller molar mass contains particles traveling at a faster average speed, and the gas with the larger molar mass contains particles traveling at a slower average speed. Question 1. Hydrogen particles are, and the answer is lighter than oxygen particles. At a given temperature, the hydrogen particles travel at a faster average speed than oxygen particles. Now I'd like to talk about the distribution of speed in a sample of gas. So here in the PhET simulation, we can see that some particles are traveling at a slower speed. Other particles are traveling at a faster speed. In a sample of gas, each particle is not traveling at the same speed. There is a range of values for speed. So in the PhET simulation, you can see with these white rectangles, on the y-axis it says number of particles, and on the x-axis is the speed. Again, some particles are traveling at a slower speed, other particles are traveling at a faster speed. So this range can be represented graphically by a Maxwell-Boltzmann distribution curve, as shown below. The peak of the curve represents the most probable speed, or the speed of the largest fraction of gas particles. Now what I'd like to do is to show you the comparison of the Maxwell-Boltzmann distribution curve for two different gases. So take a look. Here's the PhET simulation. We have a gas mixture. One of the gases is heavier and traveling at a slower average speed. That's the blue curve I'm showing you. Then the other gas has a different curve. This is the lighter gas traveling at a faster average speed. So when we compare these two curves, we can notice some differences in the appearance of that Maxwell-Boltzmann distribution curve. Heavier particles traveling at a slower average speed, represented by the blue curve. Lighter particles traveling at a faster average speed, represented by the orange curve. Let's take a look at some important differences between these two curves. The area under each curve is the same because the total number of particles in each sample is the same. But as the average speed of the particles increases, there is a wider range of values for the particle speed. The curve broadens and flattens, and the peak of the curve moves to the right. Question 2. The diagram below represents the distribution of particle speed for samples of hydrogen, which is the lighter gas, and oxygen, which is the heavier gas, at the same temperature. Label each curve as either hydrogen or oxygen. So the heavier oxygen particles are traveling at a slower average speed. The lighter hydrogen particles are traveling at a faster average speed. On this slide, you can see a screenshot from a website. I will put this link in the video description, and these are two different Maxwell-Boltzmann distribution curves. This was created in Desmos. If you adjust the variables on the left side of the screen for either the mass of the particles or the temperature of the particles, then you can watch how the appearance of those curves can change. So take a look at what happens when I move this slider and the blue curve is affected. So what I am doing is I am increasing the mass of the particles. You can see that that curve becomes more narrow and the peak of the curve shifts toward the left, indicating a slower average speed. But now as I move it in the other direction, now as the mass of the gas particles gets lighter and lighter, now the curve is getting more flat and broad, and the peak is shifting toward the right, indicating a faster average speed. Now let's take a look at question 3. The diagram below represents the distribution of particle speed for samples of helium, neon, and argon at the same temperature. Label each curve as either helium, neon, or argon. So there are three different curves. The curve that has a peak located farthest to the left, that represents the curve where the gas particles are traveling at the slowest average speed. So that should be the heaviest particles. And then on the other side, the curve where the peak is farthest to the right, then those gas particles are traveling at the fastest average speed, so they would represent the lightest particles. On the periodic table, we know that helium is lighter than neon, and neon is lighter than argon. So the heaviest gas particles would be argon, the lightest gas particles would be helium, and so these three curves should be labeled as follows. Moving on to question 4, the diagram below represents the distribution of particle speeds for samples of oxygen at two different temperatures, 300 kelvins and 600 kelvins. Label each curve as either 300 or 600 kelvins. Well, you may recall that on that Desmos activity, on the left side of the screen, you can also change the temperature and see how that affects the appearance of the Maxwell-Boltzmann distribution. Let's take a look at what happens when you change the temperature. So now I'm going to slowly increase the temperature, and we can see that the curve becomes more broad and flat, and the peak shifts toward the right, indicating a faster average speed. And now I'm going to lower the temperature, and as the temperature of the gas gets colder, the peak shifts toward the left, indicating a lower average speed, and the shape or the appearance of the curve becomes more narrow. So this would be hotter, and this would be colder. So hopefully it makes sense to you that the faster average speed will be the higher temperature, and the slower average speed would be the lower temperature. So these are the correct answers to question 4. Question 5. Place a check mark next to each of the following statements that is true regarding the two gas samples listed in the table above. So sample number 1 is nitrogen gas at 400 Kelvin. Sample number 2 is oxygen gas, also at 400 kelvins. Remember that the Kelvin temperature of a sample of matter is proportional to the average kinetic energy of the particles in the sample. And since these two gases are at the same temperature, they have the same average kinetic energy. So that's why that particular statement is true. And since we know from the periodic table that nitrogen is lighter than oxygen, then the nitrogen particles, which are lighter, are traveling at a faster average speed than the heavier oxygen particles. Now I'm going to move on to the next topic. This is topic 3.6, deviation from ideal gas law. Here is an essential knowledge statement from the AP Chemistry course and exam description. The ideal gas law does not explain the actual behavior of real gases. Deviations from the ideal gas law may result from interparticle attractions among gas molecules, particularly at conditions that are close to those resulting in condensation. Deviations may also arise from particle volumes, particularly at extremely high pressures. So first, let's take a look at the effect of interparticle attractions between gas particles. So in these two particle diagrams, on the left, we see an ideal gas at a relatively high temperature. And on the right, we see a real gas at a relatively low temperature. So we assume in the ideal gas law that there are no attractive forces between gas particles. So as this particle is about to collide with the container wall, it would experience a collision with the container wall, and pressure is the result of the collisions between the gas particles and the container wall. So what happens with a real gas at a relatively low temperature? Well, now this particle does experience some attractive forces with neighboring gas particles. And so this particle will collide with the container wall with a smaller force of impact because it does experience some of these interparticle attractions. So this is question 6 in your packet. The effect of interparticle attractions on the observed gas pressure. In an ideal gas, it is assumed that there are no attractive forces between the gas particles. However, the particles of a real gas do experience attractive forces. This effect is especially noticeable when the gas temperature is relatively low, as they mentioned in the essential knowledge statement, where you get close to the point at which the gas condenses. That would be the greatest effect, where the gas is about to turn into a liquid. The attractive forces between gas particles can decrease the force with which the particles collide with the container walls, as shown in the diagram above. This causes the observed pressure of a real gas to be less than the value predicted by the ideal gas law. Deviations from the ideal gas behavior can also arise from particle volumes, especially at high pressures. Let's take a look at that effect. So here we have two particle diagrams. On the left, we have an ideal gas at a relatively low pressure, and on the right, we have a real gas at a relatively high pressure. We assume that the volume of the gas particles themselves is so small that it is zero or negligible. Therefore, the volume of the entire gas container is equal to the free space in which the gas particles can move around. But under these conditions of high pressure, now the volume of the gas particles themselves is a significant fraction of the total volume. And so now, as a result, there is a smaller amount of free space in the container in which the gas particles can move around. So this will change the observed value of the pressure, which will be different than what is predicted by the ideal gas law. So this is question 7 in your packet, the effect of particle volume on the observed gas pressure. In an ideal gas, it is assumed that the volume occupied by the gas particles themselves is zero or negligible. The free space in which the gas particles can move around is equal to the entire volume of the container. However, the particles of a real gas do have volume and they do occupy space inside the container. This effect is especially noticeable when the gas pressure is very high. When the volume of the gas particles themselves becomes a significant fraction of the container volume, the free space in which the gas particles can move around is decreased. This causes the observed pressure of a real gas to be greater than the value predicted by the ideal gas law. All right, let's summarize this in question 8. So, question 8, a gas sample should exhibit ideal behavior at relatively high temperatures and low pressures. So remember that for these particle diagrams, we assume that the particles of gas experience no interparticle attractions, and that makes sense. When the temperature is high, the particles are moving so fast inside that container that they're not going to experience any attractions to neighboring particles. And when the pressure is relatively low, now the gas particles are far apart and the size of the particles themselves is insignificant relative to the volume of the container. So under what conditions would a gas experience deviations from ideal behavior? Well, it's going to be the opposite of that. It would be at relatively low temperatures and high pressures. So now at low temperatures, the gas particles begin to experience some interparticle attractions with neighboring particles, and under really high pressures, now the actual volume of the particles themselves takes up a significant fraction of the container volume. All right, moving on to question 9. Here we have two different gases, CH4, which is methane, and NH3, which is ammonia. Which gas, shown above, is more likely to experience deviations from ideal behavior at relatively low temperatures? Justify your answer. At relatively low temperatures, the particles of a real gas can experience attractive forces, which would cause the gas to deviate from ideal behavior. Which substance, CH4 or NH3, should experience stronger intermolecular attractive forces? Here's the Lewis diagram for CH4, and here is the Lewis diagram for NH3. Hopefully you know that CH4 is a nonpolar substance, whereas NH3 is a polar substance. In terms of intermolecular attractive forces, CH4 would only experience London dispersion forces, whereas NH3 experiences London dispersion forces. It's polar, so it experiences dipole-dipole forces, as well as hydrogen bonding, because there is a hydrogen directly attached to nitrogen. So, comparing these two substances, NH3 would experience stronger intermolecular attractive forces than CH4. So the correct answer is that NH3 is more likely to experience deviations from ideal behavior at low temperatures. So what we had to do was simply understand that under these conditions, it was about the relative strength of the intermolecular attractive forces. Now let's take a look at the effect of particle volume in question 10. Question 10. We have helium and we have xenon. Which gas shown above is more likely to experience deviations from ideal behavior at relatively high pressures? Justify your answer. So under these conditions of high pressure, the volume of the gas particles themselves can become a significant fraction of the container volume, decreasing the free space in the container in which the gas particles can move around. So which substance, helium or xenon, has a larger particle volume that is more likely to take up space inside the gas container at high pressures? Well, you know from the periodic trends that as we move from top to bottom down a group or a family, atomic radius increases. So therefore, since xenon has a larger atomic radius than helium, the particles of xenon are more likely to decrease the available free space inside the gas container at high pressures, causing deviations from ideal behavior. So this had to do with the volume of the particles themselves. And so hopefully it makes sense to you that under these conditions of very high pressures, the larger the volume of the gas particle, the more likely it is to take up space inside the gas container. All right, let's move on to our next topic. This is topic 3.7, solutions and mixtures. Here are some essential knowledge statements from the AP Chemistry course and exam description. Solutions, also sometimes called homogeneous mixtures, can be solids, liquids, or gases. In a solution, the macroscopic properties do not vary throughout the sample. In a heterogeneous mixture, the macroscopic properties depend on location in the mixture. Solution composition can be expressed in a variety of ways. Molarity is the most common method used in the laboratory, and the equation is molarity, which is abbreviated with capital M, is equal to the moles of solute divided by the liters of the solution. A solution can involve solids, such as steel or brass. A solution can involve liquids, such as a mixture of ethanol and water. A solution can involve gases, such as the air or the atmosphere. A common example of a solution is one in which a substance is dissolved completely in water, and this is known as an aqueous solution. There are two main ways to prepare an aqueous solution. One way is to dissolve a solid solute in water. Another way is to perform a dilution, in which a concentrated solution is combined with water to make a dilute solution. Note, a concentrated solution is often referred to as a stock solution. Now, let's take a look at the procedure for dissolving a solid solute in water. Suppose that a student needs to prepare 100.0 milliliters of a 0.200 molar solution of KMnO4. KMnO4 is known as potassium permanganate. Now, this particular example question is not listed in your packet, but I thought I would use it as an example as I go through the steps in this procedure. So assuming that you have a sample of solid potassium permanganate, and assuming that you have a variety of volumetric flasks, and you can choose the correct flask that you need, step 1, perform a calculation to determine the mass of solid that is needed to prepare a specific volume of solution with a specific concentration. So here in this example, we need to start with 100.0 milliliters. You might convert from milliliters to liters in your head by simply dividing by 1,000 or moving the decimal 3 spaces to the left, but I'm going to go ahead and show this as a conversion factor. So in my first step, I'm going from milliliters to liters, knowing that there are 1,000 milliliters in 1 liter. Now I'm going to convert from volume to moles. So I'm using the molarity as a conversion factor. The 0.200 capital M, that means that there are 0.200 moles of this particular solute for every 1 liter of solution. If I have to convert into grams, I would use the periodic table to calculate the molar mass. So in this example, KMnO4, that would be potassium, manganese, and oxygen. If I do that molar mass calculation, there are 158.04 grams of potassium permanganate for every 1 mole. So 100 divided by 1,000 times 0.2 times 158.04. I'm going to round off my final answer to 3 significant figures, since the molarity has 3 significant figures. So if I do this math, I get 3.16 grams of potassium permanganate. So that's how much solid is needed to prepare this solution. Step 2, use weighing paper or a small container to measure the determined mass of solid on a balance. So let's assume that I've already weighed out 3.16 grams of solid potassium permanganate. The next step is to choose a volumetric flask with a volume that is equal to the desired volume of the solution. In this case, I would go find a 100 milliliter volumetric flask. Step 4, add the weighed sample of solid to the volumetric flask. So depending on how you do this, I would recommend using a funnel. You can also use a bottle of distilled water to rinse the weighing paper or the container, and you can also use that to transfer the solid down the neck of the funnel. You would add all of this rinsing solution to the volumetric flask. And then step 5, add distilled water to the volumetric flask until it is approximately half full. At this point, this is a very important step. You want to make sure that all the solid dissolves completely before you top off the volume to that mark, that calibration mark on the neck of the flask. So, step 6, swirl the solution in the flask. You can also cap the flask and invert it several times if you need to, but make sure that all the solid dissolves completely. Step 7, now fill the volumetric flask with distilled water up to the calibration mark on the neck of the flask. And when you're getting very close, you might switch from a dropper bottle to an actual plastic pipette, so you can add drop by drop to make sure that the bottom of the meniscus on the neck of the flask is even with that calibration mark. Then seal the flask and mix the final solution to ensure that it is homogeneous. All right, the next procedure is how to prepare a solution using the technique of dilution. And just like I had done in the previous procedure for dissolving a solid in water, I'm going to show you an example. This is not in your packet, but this example will help to illustrate the steps in the procedure. So, suppose that a student needs to prepare 500.0 milliliters of a 0.100 molar solution of CuSO4, which is copper 2 sulfate. A stock solution of 1.50 molar copper sulfate is available. So we're not going to be measuring out the number of grams of solid on a scale. We're going to simply be diluting this more concentrated stock solution by adding water. Step 1. Perform a calculation to determine the volume of stock solution that is needed to prepare a specific volume of solution with a specific concentration. So the volume of the desired solution is 500.0 milliliters. The first step would be to convert that from milliliters to liters. So I'm going to divide by 1,000 as I go from milliliters to liters. Then I will use the desired concentration of the solution. In this case, 0.100 moles of copper sulfate for every 1 liter. Now I'm not converting to grams, I'm converting to volume. So what I need to do now is use the molarity of the stock solution as a conversion factor. But since I want to put moles on the bottom to cancel out those units, in this step, what I'm doing is I'm essentially writing the molarity upside down. So I'm putting moles on the bottom and then the volume in liters on the top. In this stock solution, there's 1.50 moles of copper sulfate for every 1 liter. And if I finish off my calculation by going from liters back to milliliters, now I'm going to multiply by 1,000 to do that. If I do this math from left to right, that's 500 divided by 1,000 times 0.1 divided by 1.5 and then times 1,000, my answer is 33.3. That is the volume in milliliters of the stock solution that I need to prepare this solution. I'm going to show you another way of doing this calculation, which is very common when you're doing dilutions. In fact, I'm going to call this the dilution equation. If molarity, by definition, is moles of solute divided by liters of solution, then if I were to multiply the molarity by the volume in liters, I would get the number of moles of solute. So when we do a dilution and we start with a particular stock solution and all we're doing is adding water, the result is that the more concentrated solution is transformed into a more dilute solution. But since we're only adding water, the number of moles of solute does not change in this process. So since molarity times volume equals the moles of solute, and that is not changing, then molarity times volume of the original concentrated solution is equal to the molarity times volume of the dilute solution. So I have M times V, molarity times volume, for the concentrated solution, and that is equal to M times V for the dilute solution. Again, molarity times volume. It doesn't really matter what units you use for the volume. So it could be in liters, but it could also be in milliliters. As long as the units of volume are the same on both sides of the equation, then the proportion will work out and the math will be correct. Now I'd like to show you a portion of the AP Chemistry Equations and Constants sheet. Notice that under this section, which is entitled Gases, Liquids, and Solutions, you do see the equation, which is the definition of molarity. Molarity is defined as moles of solute per liter of solution. But what you don't see on the AP Chemistry Equations sheet is the dilution equation that I just taught you. So if you know that molarity times volume for the concentrated solution is equal to molarity times volume of the dilute solution, then that's great. But that equation, the dilution equation, is not listed on the AP Chemistry Equations and Constants sheet. Okay, so if I had used the dilution equation, I would have still gotten 33.3 milliliters. Let me show you how that works. So the concentrated solution is 1.50 moles per liter. The volume of the concentrated solution is what I'm trying to find. The molarity of the dilute solution is 0.100 moles per liter, and the volume of this dilute solution is 500.0 milliliters. So when I plug in this information into this equation, and I'm solving for the volume of the concentrated solution, the math I'm doing is 0.1 times 500 divided by 1.5. And yes, I get 33.3 milliliters, which is the volume of the stock solution that I need. All right, moving on to step 2 in the procedure. You can use a graduated cylinder, a burette, or a volumetric pipette to measure the determined volume of stock solution as precisely as possible. So we're not going to use a beaker. We're going to use something with very fine graduated lines on it. So for example, a graduated cylinder, which you can typically go out to at least the 10th place for your precision of volume. Or you can use a burette, which is often marked in such a way you can go out to the 100th place. There's also a piece of equipment called a volumetric pipette, and you would typically use a volumetric pipette as a way of getting a very precise volume. So whichever piece of glassware you use, then you would choose the volumetric flask with a volume that is equal to the desired volume of the solution. In this case, we would choose a 500 milliliter volumetric flask. So now we have to transfer the measured amount of stock solution to the volumetric flask. In this case, 33.3 milliliters of the stock solution is transferred to the volumetric flask. We don't have to worry about dissolving the solid because it's already in solution form. We would add water gradually to the volumetric flask so that the final volume is equal to the mark on the flask. So you might switch over to a dropper pipette so that the bottom of the meniscus is even with the mark on the flask. Then your last step is to simply seal the flask and mix it so that it's homogeneous. All right, this is question 11 in your packet. A student needs to prepare 250.0 milliliters of 0.0500 molar sodium sulfate, Na2SO4. Part A. Determine the mass of sodium sulfate solid that is needed to prepare this solution. So since this particular calculation does involve going from moles to grams, we will need to calculate the molar mass of sodium sulfate. Again, that's Na2SO4. So when we use the information from the periodic table, that gives us a molar mass of 142.04 grams per mole. First step would be to start with the volume of the solution. So in this case, that would be 250.0 milliliters. I'm going to first go from units of milliliters to liters by dividing by 1,000. And then I will use the molarity, in this case 0.0500. That's my molarity. That is the number of moles of sodium sulfate for every 1 liter of solution. So now if I use the molar mass, I can go from moles to grams. There are 142.04 grams of sodium sulfate for every 1 mole. So 250 divided by 1,000 times 0.05 times 142.04. I'm going to round off my final answer to 3 significant figures because the molarity has 3 significant figures. So when I do this math, I get 1.7755, which will, when I round off, become 1.78 grams of sodium sulfate. So that's how much of the solid I need to prepare 250.0 milliliters of a 0.0500 molar solution of sodium sulfate. All right, let's move on to part B of this question. A student makes the claim that the concentration of sodium ions in this solution is equal to 0.0500 moles per liter. Do you agree or disagree with the student's claim? Justify your answer. So think about what happens to the solid sodium sulfate Na2SO4 when it's dissolved in water. You may recall from an earlier video, this was back in Unit 4, we talked about electrolytes and how some substances like glucose, when dissolved in water, do not split up into separate particles, but something that is ionic, in this case sodium sulfate is definitely an ionic compound, it will split up into individual aqueous ions. So we have 2 moles of sodium ions produced for every 1 mole of sodium sulfate. So therefore, I would disagree with the student's claim. Since 2 moles of sodium ions are produced in solution for every 1 mole of Na2SO4, the actual concentration of sodium ions in this solution is not 0.05, but actually twice as much. It would be 0.100 moles per liter. All right, let's take a look at question 12. We have a procedure, and it says a student was asked to prepare 100.0 milliliters of 3.00 molar potassium nitrate, KNO3. The student wrote down a description of each step that they performed in the laboratory. The list is shown above. Identify 2 different mistakes that were made in this experiment. Explain what the student should have done in order to correct each mistake. So let's go ahead and take a look at the calculations involved for preparing this solution. Like we saw in question 11, we have to calculate the molar mass of the solute. So for KNO3, that's potassium, nitrogen, and oxygen. If we use the information from the periodic table, we get a molar mass of 101.11 grams per mole. I'll go ahead and start with the volume. So 100.0 milliliters, convert that from units of milliliters to liters by dividing by 1,000. Then I will use the molarity as a conversion factor to go from volume to moles. So there are 3.00 moles of potassium nitrate. for every 1 liter of solution. And then converting from moles to grams using the molar mass, there are 101.11 grams of potassium nitrate for every 1 mole of potassium nitrate. So if I do this math, 100 divided by 1,000 times 3 times 101.11, I get on my calculator 30.3 grams of potassium nitrate. So we have just discovered our first mistake. The student should have used 30.3 grams of solid potassium nitrate instead of using 3.03 grams. Now let's see if we can find the second mistake that was made in preparing this solution. So step 3, add distilled water to the volumetric flask up to the calibration mark on the neck of the flask. Step 4, sealed the volumetric flask and mix the final solution until all the potassium nitrate solid dissolved completely. So that is going to be our mistake. What they should have done, as we talked about earlier in this video, is to add distilled water until the flask is approximately half full, swirl or mix the solution to make sure that all the solid dissolves completely. Then, after the solid dissolves completely, fill the volumetric flask with distilled water so that the final volume is equal to the calibration mark. So the mistake that they made is they filled up the volumetric flask with water to the calibration mark before ensuring that all the solid had dissolved completely. So after they had added the correct amount of solid to the flask, they should have done the following. Add distilled water to the volumetric flask until it is approximately half full. Swirl or mix the solution to make sure that all the solid dissolves completely. Then fill the volumetric flask with distilled water up to the calibration mark, and then do a final seal and mix to make sure that it's homogeneous. All right, let's take a look at question 13. It says, a student prepared a solution of CaCl2, which is calcium chloride, by following the procedure shown above. Calculate the concentration of the chloride ions, Cl-, in this solution. In step 1, they measured out 50.00 grams of solid calcium chloride. Let's convert that from grams to moles. So using the information on the periodic table, we can calculate the molar mass of CaCl2, which happens to be 110.98 grams per mole. Let's convert from grams to moles, so 50.00 grams of CaCl2 times 1 mole of calcium chloride for every 110.98 grams. And if we do this math, we get 0.45053. Notice that I'm not going to round off this answer too much because this is not my final answer, so I'll leave a little bit of extra precision in my calculator at the moment. Remember that molarity is moles of solute divided by liters of solution. So what's our volume in this case? Well, it would be 500.0 milliliters, and that would equal, when we divide by 1,000, 0.5000 liters of solution. Remember, molarity is moles over liters. So when I do this math, I take 0.45053 divided by the volume in liters, so divided by 0.5, and I get 0.90106. Again, I'm not rounding off too much because I'm not sure if this is my final answer. So let's take a moment and consider where we are in this calculation. It said to calculate the concentration of the chloride ions in this solution. So does this value, this 0.90106 moles per liter, does this represent the concentration of the chloride ions in the solution? Well, you may recall from question 11 in this packet that sodium sulfate breaks up into sodium ions and sulfate ions, and that there was this 2-to-1 ratio between moles of sodium and moles of sodium sulfate. So we have a similar situation right now. So just like sodium sulfate, calcium chloride, CaCl2, will dissolve in water and split up into calcium ions and chloride ions. So in fact, for every 1 mole of solid calcium chloride, CaCl2, that dissolves in water, 2 moles of aqueous chloride ions are produced. So that number, that 0.90106, that's not the concentration of chloride ions, but rather the concentration of calcium chloride as a whole. So I'm going to multiply by 2 since there are 2 moles of chloride ions for every 1 mole of calcium chloride. And when I do this math, I'm going to round off my final answer to 4 significant figures, since the mass, 50.00, and the volume, 500.0, they have 4 significant figures. So on my calculator, when I round off to 4 significant figures, I get 1.802 moles per liter, or you could just say 1.802 capital M for molarity. That is the concentration of the chloride ions in this solution. All right, now let's move on to question 14. A student needs to prepare a solution of aqueous sodium hydroxide, which is NaOH. Calculate the volume of 6.0 molar sodium hydroxide needed to make 500.0 milliliters of 0.100 molar sodium hydroxide. Hopefully you can tell when you read this question that we are doing a dilution. So we're not going to need to calculate the number of grams of solid sodium hydroxide. What we need is to calculate the volume of the stock solution that is needed to prepare this solution. I'm going to show you both ways of calculating the answer. So the first way involves traditional units involving conversion factors, and then I will show you that dilution equation that I mentioned earlier. So here I'll begin with the volume of the desired solution, which is 500.0 milliliters. My first step will be to go from units of milliliters to liters. So I'm going to divide by 1,000 to do that. My next step will be to use the concentration of the desired solution as a conversion factor. I'd like to go from volume to moles. So it's going to be 0.100 moles of sodium hydroxide for every 1 liter of solution. Now, instead of going into grams, I'm going to use the 6.0 molar solution as a conversion factor. So I'd like to use moles on the bottom and liters on top. That way the moles will cancel out. And then I will use the last conversion factor to go from liters to milliliters. So when I'm all done, I will calculate the volume in units of milliliters of this stock solution that is needed. So 500 divided by 1,000 times 0.1 divided by 6 times 1,000. So if I do this math, I get 8.3 milliliters. So that is the volume of 6.0 molar sodium hydroxide that is needed. Let me show you the other way of doing this calculation using the dilution equation. The molarity of the concentrated solution times the volume of the concentrated solution is equal to the molarity of the dilute solution times the volume of the dilute solution. And so I know 3 of these 4 variables. The molarity of the concentrated solution is 6.0. The molarity of the dilute solution is 0.100. The volume of the dilute solution is 500.0 milliliters. So when I do this math to solve for the volume of the concentrated solution, the math is 0.1 times 500 divided by 6. And sure enough, I get the same answer, which is 8.3 milliliters of this 6.0 molar sodium hydroxide solution. That is how much is needed to make this solution. All right, let's take a look at question 15. A student prepared a solution of HNO3, which is called nitric acid, by following the procedure shown above. Calculate the concentration of nitric acid in this solution. In step 1, they added distilled water to a 200.0 milliliter volumetric flask until it was approximately half full. And in step 2, they used a volumetric pipette to measure 25.0 milliliters of 3.00 molar nitric acid, and they added the solution to the volumetric flask. If you're wondering why they added the water to the flask until it was approximately half full. It is a good safety tip or a safety procedure to add concentrated acid to water instead of adding water to concentrated acid. So that's why they added the acid to the water in this example. So for us to start this calculation, let's go ahead and calculate how many moles of HNO3, nitric acid, were used. So volume is 25.0 milliliters. I would convert that from units of milliliters to liters by dividing by 1,000. And then I will convert from volume into moles using the molarity as a conversion factor. So 3.00 moles of nitric acid for every 1 liter of solution. That's my concentrated solution. If I do this math, 25 divided by 1,000 times 3, I get 0.0750 moles of nitric acid. So that's how many moles of nitric acid were added to the flask, and the final volume is 200.0 milliliters, which, when I convert to liters by dividing by 1,000, is equal to 0.2000 liters of solution. So what they want in question 15 is the concentration of nitric acid in this solution. Moles divided by liters will give me the correct answer. So 0.0750 moles divided by 0.2000 liters, that gives me a final answer of 0.375 moles per liter. Now, if you're wondering, could you have used the dilution equation to get this answer? And the answer is yes, absolutely. So let me go ahead and show you how you could use the dilution equation to get this same answer. Remember that the dilution equation is M times V for the concentrated solution equals M times V for the dilute solution. If you know 3 of the 4 variables, then you can use this equation. So the molarity of the concentrated solution is 3.00. The volume of the concentrated solution is 25.0 milliliters. We don't know the molarity of the dilute solution, at least not yet, and the volume of the dilute solution is 200.0 milliliters. So the math involved here would be 3 times 25 divided by 200. So the correct answer is 0.375 moles per liter. Now we're going to take a look at our next topic. This is topic 3.8, representations of solutions. Here is an essential knowledge statement from the AP Chemistry course and exam description. Particulate representations of solutions communicate the structure and properties of solutions by illustration of the relative concentrations of the components in the solution and/or drawings that show interactions among the components. Now let's take a look at question 16 in your packet. So we have particle diagrams, and it says that beaker X contains 1 liter of 2.0 molar AgNO3, which is silver nitrate. Beaker Y contains 1 liter of MgCl2, which is magnesium chloride. A student combines the solutions by pouring them into a larger, previously empty beaker Z. A white precipitate is formed. Assume that the volumes are additive. In other words, the total volume of solution is 1 plus 1, which is 2 liters. Part A, determine the concentration of magnesium chloride in beaker Y. So we are going to have to use the information in the particle diagrams to answer these questions. Beaker X contains a 2 molar solution of silver nitrate, and beaker Y contains a solution of magnesium chloride, but we are not given the molarity or the concentration. So the first thing I'm going to do is to count the number of silver particles in beaker X. So that's going to be the circle with the plus sign. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 silver ions in the particle diagram on the left. Now, when I count the number of magnesium ions in beaker Y, that would be the ones that have the +2 charge. 1, 2, 3, 4, 5. So since there are only 5 magnesium ions compared to 10 silver ions, that means that the concentration would be half as much. So the concentration of silver nitrate is 2 molar. The concentration of magnesium chloride would be half as much, or 1 molar. Now moving on to beaker Z, we can see that there's the same number of moles of magnesium ions in solution, but the volume is not 1 liter. The volume is 2 liters. So when you have the same number of moles in twice the volume, the concentration would be half as much. So the concentration of magnesium nitrate in beaker Z is going to be not 1 molar, but half as much, or 0.5 moles per liter. All right, this is question 17. The particle diagram shown above on the left represents 1 liter of 1 molar sodium chloride. Water molecules are not shown in the diagram. Part A, do the black circles in the diagram above represent sodium ions or chloride ions? Justify your answer. If you look closely, you can see that the black circles in the diagram are slightly smaller in size than the white circles in the diagram. And on the periodic table, we know that sodium has atomic number 11 and chlorine has atomic number 17. So when sodium becomes a +1 ion, it loses 1 electron. And when chlorine becomes a negative ion, it gains 1 electron. So the sodium plus ion has 10 electrons, and the chloride, Cl- ion, has 18 electrons. That is going to create a difference in size. So the correct answer to part A is that the black circles, which are the smaller ions in the diagram, they represent sodium ions. That's because sodium has 10 electrons, 1s2, 2s2, 2p6, and that would be smaller in size than the chloride ions, which have 18 electrons, 1s2, 2s2, 2p6, 3s2, 3p6. Chloride, with its 18 electrons, represents a higher energy level that's filled, so is larger in size than the sodium ions, which are only stopping at the second energy level. All right, in part B, in the boxes above, draw particle diagrams to represent 1 liter of 1.5 molar sodium chloride. So how do I go from 1 molar to 1.5 molar? That would be a change in concentration by a factor of 1.5. If I multiply 1 by 1.5, I should have the proper number of particles. So 4 particles of sodium, 4 particles of chloride. 4 times 1.5 is 6. So I should have 6 sodium ions and 6 chloride ions. So something like this drawing would be correct. And then 1 liter of 1 molar magnesium chloride. Same concentration, but a different compound. So same concentration, but a different ratio of ions. Since I have 4 sodium ions in the particle diagram on the left, I will need 4 magnesium ions in the particle diagram on the far right. But there should be a 1:2 ratio between magnesium and chloride. So I'm looking for 4 magnesium ions, but 8 chloride ions. Therefore, the particle diagram on the far right should look something like this. Now, let's take a look at question 18. A student is given a 50.0 milliliter sample of a solution of sodium carbonate of unknown concentration. To determine the concentration of sodium carbonate in this solution, the student adds an excess amount of 1 molar calcium nitrate to the solution, causing a precipitate to form. Part A, write the balanced molecular equation for the precipitation reaction that occurs between sodium carbonate and calcium nitrate. I'm going to show diagrams to indicate the charge on each ion in the reactants. So for sodium carbonate, I'm going to represent the sodium ion, Na+, and the carbonate ion, which happens to be CO3 2-, like this. So hopefully you can see that there are 2 sodium ions needed for every 1 carbonate ion. That way, the charges on the ions are balanced in that formula. So in a similar way, here is my representation of the calcium ion, which has a charge of 2+, and the nitrate ion, which is NO3, with a charge of -1. So I have 2 nitrate ions in that formula for every 1 calcium ion. That way, the charges on the ions are balanced. Now, the first product that I'm going to write is going to contain the sodium ion. Well, sodium's partner on the right side of the equation would be nitrate, which is written as NaNO3, and that formula shows that there's 1 sodium for every 1 nitrate. The charges are +1 and -1. Calcium is now bonded with carbonate, and since the charge on calcium is 2+ and the charge on carbonate is 2-, then the formula of calcium carbonate is written as CaCO3. Now, to balance the overall molecular equation, there needs to be 2 moles of sodium nitrate on the right. I would use another formula of sodium nitrate. That way, all of the ions are balanced on both sides of the equation. So here is the way I would write the balanced molecular equation. So Na2CO3 plus the formula for calcium nitrate, and then I have a 2 as a coefficient in front of the formula for sodium nitrate plus calcium carbonate, CaCO3. I have left question marks here because I want to talk about the soluble ions and which one of the products is the precipitate. You may recall from earlier videos, I think that was in Unit 4, talking about net ionic equations, that we have the so-called SNAP ions that are soluble. That's sodium, nitrate, ammonium, and potassium. So in this situation, sodium nitrate is soluble, therefore the precipitate is calcium carbonate. So I've now added AQ to show that sodium nitrate is aqueous and still dissolved in water, and then S for the solid precipitate calcium carbonate. Moving on to part B, write the net ionic equation for the reaction that you wrote in part A. Now that we know that calcium carbonate is the precipitate, that's the only chemical formula that would appear on the right side of the equation. The sodium and the nitrate ions are called spectator ions, so they would be crossed off on both sides of the equation. So on the left, we would have calcium with its charge, so 2+, plus carbonate, CO3, with its charge, 2-, and then they combine together to produce calcium carbonate. In part C of this question, we have a particle diagram, but it says the diagram is incomplete. Draw in the species needed to accurately represent the major ionic species remaining in solution after the reaction has been completed. So I see 2 sodium ions in this particle diagram, and I see 4 nitrate ions in this particle diagram. So the problem has to do with charge balance. +2 and -4 are not balanced. So if the total positive charge is not balanced by the negative charge, then we have to fix this. So we have to draw in the species that is needed to accurately represent the major ionic species remaining in solution after the reaction has been completed. Now, initially, you might think that all you need to do to complete this diagram is to add 2 more sodium ions so that the total charge of the aqueous ions is equal to 0. The problem with that is that it ignores the information that was given to us in this question. So the student had added an excess amount of calcium nitrate. Therefore, if an excess amount of calcium nitrate had been added to the solution, the particle diagram should indicate an excess amount of calcium nitrate. So what we have to do is we have to add 1 calcium ion to this diagram. Just 1, because now there is a balance of positive and negative ions in solution. The total charge of positive ions would be +4, and the total charge of negative ions would be -4. So this would be the correct answer. If you had added 2 calcium ions to the diagram, now the overall charge would no longer be balanced. You would have +6 and -4 in this diagram. So you could still fix it by adding 2 more nitrate ions, because then you would have +6 and -6. This right now would be an acceptable answer, but at a minimum, what you would need to do to give the correct answer would simply be adding 1 calcium ion to the diagram. All right, let's move on to part D. The student filters the solution and dries the solid precipitate. The mass of the precipitate is recorded as 0.93 grams. Calculate each of the following: the number of moles of the precipitate and the concentration in moles per liter of sodium carbonate in the 50.0 milliliter sample of solution that was used in this experiment. So the first thing we have to do is calculate the number of moles of the precipitate. Remember that the precipitate is calcium carbonate, that's CaCO3. So using the information on the periodic table for calcium, carbon, and oxygen, we get a molar mass of CaCO3, which works out to be 100.09 grams per mole. Let's take our mass, which is 0.93 grams of calcium carbonate, and convert that to moles. So times 1 mole of calcium carbonate for every 100.09 grams. And we get on the calculator 0.00929. I see 2 significant figures in our mass. So since 0.93 has 2 significant figures, let's call this 0.0093 moles. And you could write this in scientific notation if you want to, and that would be 9.3 times 10 to the -3 moles of calcium carbonate. Moving on to part 2 of letter D, it says, determine the concentration in moles per liter of sodium carbonate in the 50.0 milliliter sample of solution that was used in this experiment. So if you're wondering, how do we switch from moles of calcium carbonate to moles of sodium carbonate, let's remember that the balanced molecular equation looks like this. So you can see that there is a 1-to-1 mole ratio between calcium carbonate on the right and sodium carbonate on the left. Since we already know the number of moles of calcium carbonate, then that is going to be the same as the number of moles of sodium carbonate based on that 1-to-1 mole ratio. Remember that molarity is moles divided by liters. So we now have the number of moles of sodium carbonate, 0.0093. And if we take 50.0 milliliters and simply divide that number by 1,000, that would be the number of liters of solution. So moles of sodium carbonate, 0.0093. Volume in liters of the solution, that would be 0.0500. So that would be moles divided by liters is 0.186. So our answer to part 2 of part D would be 0.186 capital M, or moles per liter. Let's take a look at part E of this question. If the solid precipitate was not completely dry when its mass was recorded, will the calculated value for the concentration of sodium carbonate be too low or too high? Justify your answer. Well, since we just did the calculation for the concentration of sodium carbonate, let's take a look at that calculation and see what would happen if the solid precipitate was not completely dry. So here are the calculations. The mass of precipitate is 0.93 grams, but what if the solid precipitate was not completely dry? Well, there'd be excess water. That would cause the mass of calcium carbonate, the precipitate, to be too high. Therefore, the calculated value for moles of calcium carbonate would also be too high. This would also cause the calculated value for the moles of sodium carbonate to be too high, and thus the molarity, the calculated value for the concentration of sodium carbonate, would be too high. So to summarize, the presence of water in the solid precipitate, that will cause the measured mass of calcium carbonate on the scale to be too high. As a result, the calculated number of moles of both calcium carbonate and sodium carbonate would be too high. Therefore, the calculated concentration of sodium carbonate would be too high. All right, there's one more part in this question. This is part F. After the precipitate has been filtered from the solution, the liquid that passes through the filter paper is tested to see if it can conduct electricity. What would be observed? Justify your answer. So here we see in the particle diagram that the solid calcium carbonate is on the bottom of the beaker, and in solution would be the aqueous solution that contains sodium ions, nitrate ions, and calcium ions. So if you test this solution for conductivity, then yes, it would conduct electricity because there are aqueous ions present in the solution. So a solution that contains aqueous ions is going to conduct electricity. All right, well, this was the final part of question 18, and question 18 was the last question in this packet. So this is the end of the video for topics 3.5 to 3.8. I hope that you found these answers and explanations helpful. Thanks for watching.